Okay, so let's head to the very frontiers of particle physics. We're down at the Large Hadron Collider, and we are smashing protons together at just ridiculous speeds, nearly the speed of light. We're creating this whole universe of exotic particles, but all of this incredible power, it also creates a brand new, fascinating challenge.
And that's really the big question we're tackling here. See, we can create these massive, heavy particles. Think of the Higgs boson or the top quark. But they're gone in an instant. I mean, they exist for such a tiny, tiny fraction of a second that there's no way to see them directly. So how in the world do we prove they were ever there to begin with?
Well, the answer is we become detectives. We look for the evidence they leave behind. When one of these heavy particles decays, it basically explodes into a spray of more common, stable particles. And this spray, it shoots off in pretty much the same direction as the original particle, creating what we call a jet. So we can't see the parent particle, but we can see its jet. It's the footprint it leaves behind.
Now, for a long time, this method of looking for jets worked great. It was fantastic. But as our colliders got more and more powerful, the pictures started to get, well, blurry. With the insane energies we're reaching at the LHC, a whole new problem started to creep in.
You see, we're not just creating these particles sitting still. They are often shot out of the collision with a huge amount of momentum, flying sideways at speeds that are truly relativistic. The term physicists use is that they are highly boosted. And that boost, well, that changes everything.
And you can really see the problem right here. In a lower energy collision, maybe a Higgs boson decays into two B quarks. You get two nice, distinct jets. Easy to tell apart, right? But now look what happens when that same Higgs is boosted to a super high energy. Those two sprays of particles get squashed together into one big, messy, overlapping cone. And that's the heart of it. The source material puts it perfectly. The decay products become collimated. It's just a fancy way of saying they get squeezed together into a really narrow beam. This collimation is the source of all our trouble.
So this new messy object is what physicists started calling a fat jet. It looks for all the world like a single jet, but it's not. It's actually two or maybe even more jets all merged together. It's like a crime scene where all the clues have been smeared into one big blob. And now it's incredibly hard to know if you found a decaying Higgs or just a regular boring old jet.
So for a little while, it kind of seemed like these boosted events were a lost cause. A part of the data that was just too messy to even bother with. But then, physicists had this absolutely brilliant shift in perspective.
They started asking a totally new kind of question. Instead of just throwing these fat jets away, they started to wonder, what if we're just not looking at them the right way? What if this mess isn't actually random at all?
And that was the key. The breakthrough idea was to stop treating the fat jet like one thing, and instead start looking for the original individual jets that were hiding inside of it. What if we could somehow peel back the layers and see its internal plumbing?
This idea gave birth to a whole new field of analysis called jet substructure. It's essentially a toolbox full of clever algorithms that are designed to peer inside a fat jet and pull apart its different components. It's like giving physicists a new pair of super-powered glasses that can take that blurry, smeared-out picture and snap it into sharp focus.
So this new technique sounds cool, but how was it actually used? Well, it wasn't just some theoretical game. It had a huge, spectacular, real-world application, the hunt for maybe the most famous particle of them all, the Higgs boson.
So the Higgs boson actually decays into a pair of B quarks most of the time. The problem was that signal was totally buried under a mountain of background noise. Everybody thought it was a lost cause. But the work of physicists like Butterworth and his team showed that by specifically looking for a boosted Higgs inside a fat jet, they could bring this crucial search back from the dead.
So how did they do it? How did they pull it off? They found a smoking gun. They found a simple, predictable signature that was hiding in plain sight, right there in the apparent chaos of the fat jet. Turns out, the physics of a boosted decay leaves a very specific clue behind. And that clue is this beautiful inverse relationship. As the parent particle's sideways momentum, what we call p-perp, goes up, the angular separation between the things it decays into, what we call delta r, goes down. It's really simple. The faster you throw the particle, the tighter the spray of its debris. And this wasn't just some vague idea. It's a predictable mathematical relationship. You can see the formula right here. That angular separation is roughly equal to twice the Higgs mass divided by its momentum. This was the secret code. By measuring the properties of the stuff inside a fat jet,
Physicists could check if it matched this exact signature. If it did, bingo, they knew they'd found a boosted Higgs. So what's the big picture here? What does this all mean? Well, this wasn't just some clever one-off trick to find a single particle. The development of jet substructure was a total, fundamental shift in how we look at data from the LHC.
I mean, this completely changed the game. It brought back searches for the Higgs that everyone thought were impossible. It gave us the tools to finally tell the difference between these super interesting boosted objects and all the boring background noise. Jet substructure is now a standard, powerful part of every physicist's toolkit, and it's opening up this whole new window to search for particles we haven't even dreamed of yet.
And really, that's the thought I want to leave you with. By learning how to look inside the chaos, we found the Higgs boson. So it just makes you wonder, what else is in there? What other new particles, what new secrets of the universe are hiding inside these jets, just waiting for us to find the right way to look?